All right, here we are in Chapter 6, Normal Distribution. We're going to start 6.3 this time. And it's the central limit theorem. This adds another little layer of complexity to what we've been doing in this chapter. This time, we're going to talk about how we use this central limit theorem to solve problems involving samples and using the sample mean or the sample average from a larger sample. So this is the central limit theorem. I'm sure it's in your book. In addition to knowing how individual data values vary about the mean for a population, statisticians like to know how the mean of the sample or the averages of the sample when the samples are of the same size taken from the same population vary from the population mean, because a sample is different from the entire population to some extent. So we have what's called a sampling distribution of sample means. So that's a mouthful. And it's a distribution obtained by using the averages or the means that are computed from random samples of a specific size taken from a population. And then sampling error is the difference between the sample measure and the corresponding population measure, due to the fact that the sample is not a perfect representation of the population. So again, how is the sample different from the overall population measure? Because it's a smaller set of data than the larger population data. Now, properties of this distribution of sample means. What we're going to see is the mean of the sample means, the average of the sample averages. If you take all the sample averages and list them and then average that, that's going to be the same as the population mean. And the standard deviation of those sample averages or sample means is going to be smaller than the standard deviation of the population. And it's going to be equal to the population standard deviation divided by the square root of the sample size. So we've got different formulas for the standard deviation for this distribution of sample means than we did in with a population. So as the sample size n increases, the shape of the distribution of the sample means or the sample averages taken with replacement from a population with a mean of mu, which of course is a symbol for the population mean, and a standard deviation of sigma, will approach a normal distribution. So the larger the sample size, the more we can assume that it has follows that normal distribution curve. And usually 30 is the number that we go by. If the sample size is 30 or bigger, we assume that it has that normal distribution shape. If it's less than 30, then you usually want to see in the problem that we're going to assume the normal distribution or something to that effect. The mean of the sample mean equals the population mean. So this is something that you can assume here. This is something you'll assume, that the mean of the sample is equal to the population mean, and the standard deviation of the sample, which is called the standard error of the mean, there's a formula listed here at the bottom. And this sigma x bar, sigma with a subscript of x bar, is that standard deviation of the sample means, x bar being a sample mean. And that we get that by doing the sigma of the population divided by the square root of the sample size. So the central limit theorem will answer questions when we have a sample of a population. And so we're going to look at how that wording looks as we go through these problems. But the process is very much the same. You get a z-score, you read from the z-table, but now we have a new formula for z-values. So with this central limit theorem, when you've got, and the key is that there's going to be the word sample somewhere, okay? You're going to see the word sample in there in your problem. And so we have a new formula for that z. Okay, this is the formula for this z. And you need to memorize this. It's x minus mu sub x over sigma sub x bar. But this right here is the formula you're going to use more often, because we learned in the slide before that the way you calculate this sigma, the standard error of the mean, is going to be sigma over the square root of n. That's the standard deviation for the sample. All right, so let's work some problems. It's always good to have some problems to go by. Here's A.C. Nielsen reported children between the ages of 2 and 5 watch an average of 25 hours of television a week. So mu is 25. Okay, our mu is 25 hours. Assume the variable, again, see here we got assume the variable is normally distributed. That tells us we can use this bell curve, this shape, okay? And the standard deviation is 3 hours. So our sigma is 3, okay? 20 children between the ages of 2 and 5 are randomly selected. So my n is 20. Find the probability that the mean of the number of hours they watch will be greater than 26.3 hours. So this is also equal to, remember, the mu of our sample, mu of x bar. So we can draw, you can draw your own standard or normal curve, drop a line down here in the middle and write the mean. The mean of the sample is the same as the mean of the population. And then we're shooting for this score, 26.3, which is bigger than the mean, so we put it right here on this side, and shade the area that we're looking for. We want to know the probability that they're going to watch greater than 26.3 hours. So kind of draw your own thing. List these variables over here that are given in the problem, then draw your own curve, mark what you're looking for, shade the area you want, and then once you do that, then you can go to work doing the calculations. So let's go on to our next slide. We're calculating the probability for a sample mean, so we have to use the central limit theorem formula, which is this that I told you we would use from the slide before. Again, you need to memorize this formula. Write it down somewhere and be sure you know that this is when you have a sample, and you know that because you've got the square root of n and you've got your others that you worked with in 6.2 that had to do with the population. So we've got to get our z-score. Well, it's x bar minus mu, 26.3 minus 25, divided by 3 over the square root of 20, and that equals 1.94. Then you're going to go into your chart just like we have before, and we're going to look up 1.94. So here's 1.9, come down here at 4, and we're right there at 0.9738. So we go back up, verify. Here's your 0.9738. That's the area under the curve. But remember, that is this part to the left of that z-score. We had a z-score here. It's 0 at the mean and 1.94 if we replace those numbers with z-scores. We want the area to the right. Well, the whole thing is 1, which is where this comes from, right here. So 1 minus the 0.9738 equals 0.0262. So the probability, again for percent, we're going to move that over 2 decimal places. The probability of attaining a sample mean larger than 26.3 hours is 2.62%, if you want to leave it a percent. Okay, so let's move on. Next example is on page 335, 614. Vehicle age. The average age of a vehicle registered in the United States is 8 years or 96 months. Okay, so we're going to write our mu here. Okay, 8 years or 96 months. Okay, that's our average. Assume the standard deviation is 16 months, so our sigma is 16 months. So we're going to be sticking with the months, it looks like. So we'll use this one we'll use that one for our average, which is what's right here. We want to know, we have a random sample, so n is 36. So when we see a sample size like that, remember we need to use that formula where we don't use the population one, we use the one that has the divided by the square root of n to calculate the z-score. And here, remember what I told you, if the sample is 30 or larger, you can assume a normal distribution. You don't have to see that word in there, and it's not actually in the problem. So we have a random sample of 36 vehicles. We want the probability that the mean of their ages is between 90 and 100. 90 is below the mean, so it's going to have a negative z-score. 100 is above the mean, so it's going to have a positive z-score. So draw your curve, place your average in the middle, your 96, and then mark these somewhere to the left and right of the mean. Once you get that drawn, go calculate your z-scores. So let's go on. And here is our 90. Remember it's, whoops. I'll go back. There we go. Okay, remember we have x bar minus mu over sigma divided by the square root of n is what is z. Okay, so that's that formula that you're going to need to remember. So x bar minus mu divided by sigma over square root of n, we have negative 2.25 here. If we just go ahead and fill in our z-scores. Our mean is always at 0, and our positive z-score is 1.5. Okay? Now, this area we're going to find here is from there to the left. This area is going to be from that score to the left. So to get this part in the middle, we need to subtract the two. So we're going to go forward. We have a negative 2.25. So here's negative 2.25 right here. 0.0122. Okay. And that's what we find here. And then a 1.5. So 1.5 is right here, 1.50, 0.9332 if I round it to 4 decimal places. So 0.9332 minus 0.0122, and that gives me the area under the curve here of 0.9210. That's that shaded area, which then in percent for probability is 92.1%. Okay. Looking at another problem. Example from page 336. Meat consumption. Average number of pounds of meat that a person consumes per year is 218.4 pounds. So that's our mu. Okay. Assume the standard deviation is 25 pounds. And the distribution is approximately normal. Find the probability that a person selected at random consumes less than 224 pounds a year. So we mark the mean. 224 is a little larger than that. But wait a minute, there's no sample size. What's the deal here? Okay, this must mean we go back 262. And so when we go forward to look at that calculation, we go back to our original z score, x minus mu over sigma. 224 minus 218.4 over 25 equals 0.22. So this score, z-score here, 0 at the mean, 0.22 here. We need to know less, so we're going to read left of that. And I'm not sure I put a chart. No, I didn't. So we're going to assume that we can look this up in the chart. And it's 0.5871. So this area is 0.5871. And so for one person, the probability of one person consuming less than 224 pounds of meat would be 58.71%. Okay. Now let's look at another problem. And I want you to notice the difference in this next problem. Here we had, this is the one before that we just did. Find the probability that a person selected at random consumes less than 224 pounds per year. There was no population, no sample. There's a population, there's no sample. You've got a mu here and a sigma here. No sample size. We go forward to this next piece. We have the average number of pounds of meat that a person consumes. We have a mu, still at 218.4 pounds, and a sigma at 25. But now, if a sample of 40 individuals is selected, now we've gotten a sample size. Find the probability the sample mean will be less than 224 pounds per year. Now we're at this central limit theorem formula. We notice that the standard deviation, this curve is much narrower. Remember, the standard deviation of a set of sample means is smaller than the population standard deviation. Now, I'm not going to count off if on a test you have problems back to back and you don't draw this curve narrower, so don't get paranoid about that or anything. But it is drawn this way on purpose. It's drawn this way because the standard deviation of this sample, this collection of sample means, is narrower, like I said, than the standard deviation of a population. Let's go forward and do our calculation. We have x bar minus mu, which is 224 minus 218.4. The standard deviation, 25, divided by the square root of n, which is 40, and we get a z-score of 1.42. The area to the left of 1.42 is 0.9222, and I'm going to assume that you could get into the table and read that yourself. So the probability, so that means we want to the left, so this whole area here is 0.9222. Hence, the probability that the mean of a sample of 40 individuals is less than 224 pounds per year is 92.22%, or you can list it as a decimal. Either way is fine. Finite population correction factor. I'm putting this on here because it's part of the chapter, and it's possible that some of the homework problems that were assigned by Miss O'Brien have this on there. This will not be on the test, okay? Will not be on the test. Okay. So don't worry about memorizing this formula, but I want you to see it. When you have the formula for standard error of the mean, it's accurate when the samples are drawn with replacement or are drawn without replacement from a very large population. A correction factor is necessary for computing standard error of the mean for samples drawn without replacement from a finite population. And also if the sample size is very large. as opposed, if the sample size is large compared to the overall size of the population, then you have to have this correction factor. So if you have a finite population, if they give you a sample of 40 out of 100, well, that's a pretty healthy percentage of that population. It's not large enough, so you would probably have to have this correction factor. And the correction factor looks like this. N is the population size. It'll be given. So, if I said my population was 100 and my sample size was 40, then you would calculate this overall would be the square root of 100 minus 40 over 100 minus 1. And so that'd be 60 over 99. You take the square root of that. And that would be your correction factor. You do that in your calculator and get a number. And then what you do is you multiply that correction factor by the standard error of the mean. And so that has to be adjusted. And so in other words, your denominator, instead of just being sigma over the square root of n, it would be, you'd have your, when you did your z-score, it would be x bar minus mu, and then you'd have your sigma over the square root of n, and you'd multiply that by the n minus n over n minus 1, this. And that mu is a pretty sorry looking mu, so let's see if I can make it look better. X bar minus mu. Okay. So, this is the sort of thing you'll have if you have a limited population and a pretty large sample taken from that population. And I kind of think that some of the problems at the end of your homework will be this, will involve using this correction factor. Again, though, it doesn't hurt you to use it, doesn't hurt you to work those problems and get the right answer, but I'm not going to put it on the test. Okay, this shows you what I just showed you. I didn't realize there was another slide. Okay, you can just see that's how you would get your z-score or z-value if you had that situation. It's what I just wrote, except it looks much neater because it's typed. All right, that's the end of 6.3. And get to work for this week on 6.3. And I'll try to get 6.4 posted towards the end of the week.